Yeah, hi, my name is Björn Erlingsson here. I'm coming from the Earth observation. We would not call it industry, but angle of view. I'm here with a presentation a little bit on a history on the CI's observation and analytics of CI's processes. I will do, as I say, this is a history chapter on 30 years. That is the playing with the title Iceland Space 30 years, and you will hear gradually why I call it a history. And maybe we can learn a little bit from it, how we can speed up things or how things evolve indeed in reality. So let me go further here. I think okay, this is not working. So the pointers here are okay. Verð ég að standa þarna eða hvað? Yeah, this is the overview of the talk, and okay. And first a little bit about myself, and then why ice, to give the backdrop, and why it's relevant, and what is relevant about it, and then the space history at the end to make the point, and a little bit into the future with the Arctic tools. And my name is Björn Erlingsson, as I said, and freelance scientist, research on sea ice from 1984, and focus on forces in sea ice and impact on sea ice growth in the Arctic. And my education is in physics and oceanography. It's not relevant here. I will try not to have this into a lecture on ice physics. My affiliation is the University Center of the Westfjords, and partly also Space Iceland. So in sea ice, it's all about ice thickness. Sea ice makes the environment and makes the land out of the sea, and its thickness is and age is kind of the prominent parameters. And then why Iceland? If we look at this image here, this is image on production in the seas. So we see the sea ice north of Iceland, and the green flakes around Iceland show primary production. If you look closely into this picture, you see that there's a feast on biological activity around the ice, and the ice from the Arctic is feeding the ocean around Iceland with food and for fishes and for haddock, herring, and cod and whales. We see also here, this is the climatology of the oceans around Iceland at 200-meter depth. And we see that there's a frontal area, it's very cold, below zero partly, in the Greenland Sea, north of Iceland, and we have a warm front in south of us and west of us, up to 5, 6, and even 8 degrees further south. So this ice stream from the Arctic kind of defines the environment in Iceland. Well, I will maybe take those videos at the end due to problems with the settings here, and I'm just talking about and what in ice we're talking about. We're talking about fractures and leads, and this ice is not as we see it on lakes, where it is not where there's hardly any fractures, and due to the winds and currents it's broken up, and I'll show you a little bit later that that has a huge impact on how it works in the climate system. So this is about Arctic sea ice, and this is very demonstrative of what is going on in the Arctic. We have sea ice area on the y-axis in September, and on the x-axis we have the cumulative CO2 emissions since 1850. So we see that a direct response of the Arctic ice to the cumulative CO emissions, and that is due to greenhouse effect, but that's not enough to explain this rapid decline. And we have changes in the climate system that affects the drift in the Arctic to some extent, but we must also recognize that the cumulative CO2 emissions are metrics for all kinds of industrial activities around the globe. So the impacts can be. I will take this video afterwards, and even this one here. We see a decay in the volume of the ice throughout the years. They started in 1980 and into 2021. And we see that this has been rapidly falling down after 2000, but in the recent years we are kind of reaching some bottom. There is not much left, so it has to be, and still the light is off in the winters, and we have a coreless winter in the Arctic, so it was always freeze there during winter. So it takes much to have it disappearing at all. So what is it about? Here we see a picture of a ship in the ice that was pressed due to forces in the ice, and that is what the science have been I'm articulating here, working on is the forces. The ship is about 10,000 tons of wet brutto tonnage, and it has been lifted up 2 meters due to the pressure in the ice, and hardly any blocks. It takes a lot of pressure to take a big ship like this, 40 meters long, and lift it up 2 meters from the waterline. And we see that the ice blocks down there are hardly any breaking much, but they are broken. This image is of leads in the ice, where it's yellow. There is a lot of them. There is a lot of openings, and even if we focus in on the dark areas here, there are also leads there, and they are very prevailing part of the Arctic. And where the light colors are, there is a lot of exchange between the atmosphere and the ocean. So we see from this picture also evidence of that the heat exchange between the atmosphere and the ocean through the ice is also in the subpolar regions or in the boundary areas, not in the central Arctic as much as it is in the others. So that's important to note. But this is, as I said, the ice flows and ridges, and this is how it can look in the ice, and looks most of the time. The ice is over 80% of the volume has been undergoing some mechanical thickness changes. So it's not thermodynamical process, but it's a dynamical process of deformations in the ice. And we see here frequency of thicknesses from 0 to 10 meters. And we see that the most frequent is about 2 meters. And just to note that it's impossible to make all this thicker ice than, say, half a meter to 1 meter without forcing it to break and raft and ridge. I'll not go very much into the detail there, but here is a profile of 4,000 meters of ice with thicknesses, and we see that mechanical processes are really the ruling factor in shaping the thickness of the ice. Well, and something there, ice brings biomass around in the Arctic, and the old ice has a lot of ice algae, and there's life under ice, small shrimps and polar cod, and whales are feeding there, and there's a feast. And even so, when it opens up, there is a huge biological activity in a small opening. Here, birds are really feeding there, and there's a lot of them. You cannot tell how many there are. So that brings me into space. Again, as I say, space is for me Earth observation. I look into space from Earth. That's why I started with the process of what are we looking for, and what kind of meaning it has for us. And radar satellites which ping the surface and take the return. They use multiple pings to enhance the signal and get a very detailed backscatter images from the surface. And there was a satellite in the CSAT in 1978 and to 1978, and it's part of the debris which has been we have been presented here previously, and it ceased to operate after 105 days. So this CSAT satellite in 1978. It really changed the picture. And you see there, just before it ceased to work on the dark images there, you see a backscatter images with 3 days apart. They look very similar, and the first thing about it is it really looks strange, and you have a lot of features in the surface that doesn't look like ice, but the most important part is the picture down below. When you take those two pictures and compare them, then you see that there are huge areas of ice flows. The squares here are 4 kilometers across. It's 100 kilometers across. So this was a new insight the satellite gave into what is going on in fracturing and deformations in sea ice. The second thing about it is that you don't see those lines. Those lines here are really independent on what's on this picture here. This means that there are some very new processes going on, and the astonishment over those processes made us, or me at that time, or nobody else looking at it, to ask the question: this this has to be explained in a simple way. If you have something in the ice that is a straight line over 100 kilometers plus, there is some physics behind it. There are some mechanics, and they have to be. It has to be possible to explain it in real terms. It's like you can have it on your desk or even in your palms. And that question triggered the whole thing, and I will not go into how that was, but the essence of it is that the ice is breaking, and while interacting, the elements are subject to breaking on both sides of the deformations. So they are moving and breaking, and there's the same material on the both sides, and it has implications. Those geometries have implications that can be studied. I will not go into that here, but at that time in 1988, I wrote a paper. We have a timeline on references from 4 to 8. From I think it is here 1991 and to 2021. So this has been in the literature. You would normally think that such innovative ideas would pop up and live for 10 years, but not for 30 years. But now it is coming back, and we are seeing more detailed fracture patterns and very sophisticated techniques in detecting them. And you can see a network of deformations there. They are not along straight lines. They are also curved if you over larger area, and you can derive information from its curvatures. And those can be extracted. They can be used to extract information about the forces in the ice field. And that is a new thing. I have the forces in the ice canopy on a geophysical scale, and we are opening up on that in a project called Arctic Tools, which is a consortium that is now developing a bid for a Copernicus call proposal. There are 10 partners, high stakes and high excitement about this, and participation from leading stakeholders in Europe, and they are from industry, public organizations, and academia as well. And it's about 4 years and 3 million euro total budget target in this. We are talking about science here, or to take a science and demonstrate a product on a technological readiness level 5 to 6, meaning that we are going for an application, a user application for a wide spectrum of users. It can be on climatology in the Arctic. It can be deriving statistics on actionable data for shipping. It can be for forecasting, and also for monitoring and risk assessment on ice. Let me see. I skipped. And this is the project, the Earth Observation and Analytics Innovation in Copernicus, and it's assimilation of new ice stress data using satellite imagery, atmospheric ice ocean model, and in situ data. So that is the combination. That is the fairy tale or the new era in space. We call it Space 4.0, that we have large processing power. We have very detailed and sophisticated satellite data, and the models are getting more and more detailed and sophisticated, and actually they are starting to resolve those. Lead patterns in a way, and those can be used to adjust the models into giving a better picture and for having not a better picture, but the only way to get a forecasting power out of this is to use models. And in-situ data is always needed. And we are also in this project developing stress sensors for transmitting ice stress measurements over satellites in real time. And then is the power of, the third component is the power of machine learning, is that by combining hybrid models, tracking variables in atmospheric ocean models that we know have to do with the formation processes in the ice, the thickness redistribution, then we can use much richer data set for machine learning training of ice classification. And not just that, for ice classification we can use high resolution backscatter imagery from the radar satellites to increase the resolution. So there are it's the second loop in improvement of the data. So this concludes, let me see. There is an initiative from ESA called Icy Moons, and this is from Europa, one of Jupiter's moons, and we have fracture patterns there, and those. This looks more or less like an ice flow field there, the left one, but the height of the ridges are not just a couple of meters as it is in the ocean. They are up to 500 meters high. And the gravity in Europa, Jupiter moons is about 13% on the Earth. And we see area in the Vatnajökull on the south coast of Iceland, where those forcing systems generating the cracks can be studied in a very high detail, because the gravity and the pressure forces are very well known there. I promise not to go into the details. But this is for the next generation. We are jumping and dancing on the image there on the lower right corner, where in the background you have those fracture patterns, and the mission to Europa is to be launched in 1 or 2 years. But when we have pictures from there, those patterns can be studied with more. And there are features here in this picture that are really exciting from a scientific point of view, and to searching analogies in the outlet glaciers in the sea ice field. We are going into deep space as well with this. So this concludes the circle. Started on ground to the satellites, and from the satellites and down and up to space again into one of Jupiter's moons of Europa. So this was a roundup of a 30 years story that started with very new data. Started first, this isn't like we are describing it, this is something new, and asked, as a scientist are supposed to do, very basic questions and go to basic first principles when we have problems, and we have to take all the crap away and say, let's start again, and then came up this 30-year story. So this was a game with words, Iceland, Spaceland, ice-land, and why it is important it's important for the globe, and also for particularly in Iceland. I mean, the Arctic really defines how living is in Iceland. We don't see it at the coast, but it really puts up the shape for the environment around Iceland. Okay, this concludes my talk. I have the video. I will just put them up as I can put up one. I will make an attempt to lock it up if it works here. I didn't want to. Let me see. Let me see. Yeah. Is the mouse working here? No. Let me see here. Yes, and if I can.
I can help you with that.
If you can put this on, this is a very interesting. This is Greenland here. This is the Arctic ice. We start here in 2016, and it is moving and breaking, and all those formations. So when it breaks up here, the exchange between the atmosphere and the ocean is 3 to 4 orders of magnitude higher than here in the ice where it's not broken. So it really is a huge impact, and when it opens up here, this is a very interesting biological area here around us. It has impact on the natural habitats. You can reload it. Natural habitats on biological activity when it opens up here. And the ice is also old ice with a lot of ice. Also, there's a lot of food there also. It's not just this ocean to breathe, but there's a lot of food. And it's quite interesting to come into this into the Arctic and see this unfriendly, hostile area. So when you look closer, there is a lot of living creatures around there, and even shrimps on have turned the bottom up, so to say. They live underneath the ice with the bottom up, not down. And there's a cod eating the shrimps there that has evolved into with a special with its head smaller. So quite interesting. And this is west of Greenland. On the other side, there is a lot of feet of ice into the Icelandic waters, and it really puts food for the fish around Iceland. So that's why we are here in a way and live here, sustain our living. Okay, this was extra. Thank you very much.